Okay, 3, 2, 1, it's jam.
What's up, science fam? When it's dark, we can't see anything. If there's no light, there's absolutely nothing you can see. It's just pitch black. But how do we see with light? What exactly is it about light that lets us see the things around us? That's what we're going to talk about in this session. My name is Sir Ramon, and this is Science with Sir Ramon. Let's do this. So, our topic for this session is light, its properties and reflection, and how it allows us to see. These are the objectives we have. The properties of light as a wave particle. We're going to discuss how light is scattered by different things, discuss the theoretical and experimental evidence of light's wave nature, explain the Ray model of light, and talk about how mirrors, plane and curved mirrors, reflect light. So first, what is light? Is it really just an electromagnetic wave? According to Isaac Newton, light is comprised of colored particles. So it's not a wave, it's a particle. So he called them corpuscles. So they're actual things. They're matter. They're like atoms. And they're going around with lots of energy. That's what Isaac Newton thought. Then, another guy named Christian Huygens, he thought of light as waves that rippled out in all directions, just like when you make ripples on the surface of water. So for him, light is a wave, not a particle. So his principle, Huygens' principle, is that each point of a light wave can be the source of a wavefront. That means that when light is traveling in a wave, if you put a slit or a tiny hole there and the light goes through that hole, it'll propagate as a wave once it goes through that hole. That means that light would bend if it goes through a certain small hole or small slit. And that's why this guy, Thomas Young, he conducted experiments with narrow slits that showed how light disperses through them like a wave. So he gave the proof that light does function like a wave. So James Clerk Maxwell, which we already discussed before when we discussed electromagnetic waves, that he unified electricity, magnetism, and light, and that's how we know that light is in fact an electromagnetic wave. So all evidence points to light being a wave, and that's how it went for a long period of time until this guy came up and said that light isn't just a wave. This guy, Albert Einstein, explained how light could excite electrons depending on its frequency through what he called the photoelectric effect. The thing is, if light is just an electromagnetic wave, it can't be able to excite actual particles in the form of electrons. So Albert Einstein said, why not? Why can't light be both a wave and a particle at the same time? He called them photons. This is one of the things he earned the Nobel Prize for, the photoelectric effect. And so, going from Einstein's theory, we now know that light has a dual nature. Thanks to quantum theory and Albert Einstein, we call light a dual wave particle. It's both a wave and a particle at the same time. So how does that work? So again, Newton thought light was made of particles because light doesn't bend around corners as far as we can tell. If you shine a flashlight on a barrier, this is how it looks like. It just has a straight line through it. However, we know that light is made of waves because of Thomas Young's experiments, and this is how he proved it. So it only bends slightly around corners, so Thomas Young had what we call a double slit experiment. There are two slits here, the 1 and the 2. And because of that, in his experiment, when light went through those slits, there was what we call interference. There's two types of interference, constructive and destructive interference. That just means that in constructive interference, the waves are building up, causing bright spots of light. On the other hand, in destructive interference, the waves are interacting in a way that is destroying the waves. They're in opposite amplitudes, such as shown in this image here. The opposite amplitudes actually cancel out, making the pattern dark. So there's bands of dark and bright that show an intensity distribution curve. Basically, Thomas Young's two tiny slits, proved that light does in fact function as a wave. So because of that, we can describe some of light's characteristics based on the characteristics of a wave. So the wavelength of light actually determines the color of light. That's why we see different things as different colors, because of the different wavelengths of light that are present in natural light. Amplitude is the brightness of light. So light intensity, how bright a flashlight or a candle is actually related to the amplitude, or how far the wave is from the normal line. And the frequency determines the energy of light. So that determines whether it's visible light or ultraviolet light and so on. Okay? But when it comes to mirrors, what nature of light prevails? So mirrors are things that reflect light. So waves are hard to explain, while particles might give the wrong idea about light's nature. So the diagram that we use to keep the dual nature of light is the ray model of light. So light rays will follow the direction of particle motion and are perpendicular to its projected wave fronts. In other words, it's just a fancy way of saying arrows have the least number of problems when we're trying to talk about light. So the main thing to take away from the ray model of light is that the eyes, how we see, is that light is focused on our eyes. So the different light rays that are going to our eyes are giving us different wavelengths of light, different colors of light that we see. So when we talk about the different colors of light, what actually reaches our eyes then is something that is reflected off of a surface. So different things reflect different wavelengths of light, resulting in different colors. So how do mirrors themselves reflect light rays? How do we put that into a diagram? So we have what we call the law of reflection. So in the law of reflection, we have different types of rays. We have the incident ray, which is the ray that is coming towards the mirror, and the reflected ray, which of course is the ray that shows the reflection of light. Now, if we have the incident and reflected rays, we have the angles between them. So this line, the normal line, is just the line that is perpendicular, forming a 90-degree angle with the surface of the mirror. Okay, so if we take that normal line and use it to split the angle of the incident and reflected ray, we have two equal halves. We have the angle of incidence, the angle that the ray is coming towards the mirror, and the angle of reflection, the angle that the ray is reflected off of the mirror. And if you look at those, they should always be equal. So the law of reflection is that the angle of incidence is always equal to the angle of reflection. It just means that the angle that a light ray hits the mirror should be equal to the angle that it bounces off. Simple. What if it's not smooth though? How does light get reflected off not smooth surfaces? So we actually have two types of reflection. We have specular reflection, which is on a real true mirror with a smooth surface, and it forms a real image because all wavelengths of light are perfectly reflected by the law of reflection. On the other hand, on diffuse reflection, if your surface is not entirely smooth, it's not super duper smooth down to the minute level, it will just diffuse the light in different directions, so you won't get a real full image. These are the surfaces that don't form actual images. So when you look at different things in your room and you see the light coming off of it, but no real image coming off of it, it's actually because there's diffuse reflection going on. There's tiny imperfections on the surface so that the light will only reflect in different directions, so you only see color, not a real image. So again, the colors of light that are reflected depend on what the material absorbs and what it reflects. What it reflects will be the wavelengths or the colors that you will be able to see. So how do images form? So let's focus on images and mirrors. So plane mirrors would form what we call virtual images. They always form virtual images. These images are what appear to be behind the mirror. So they only appear to form but light does not actually reach that place. So if you look at a mirror, if you look at yourself in a mirror, light isn't going to where it seems the image is. The image looks like it's behind the mirror, like the mirror is a window. But we know that mirrors aren't windows. There's no light actually reaching that place. So it's not a real image, it's a virtual image. A real image, on the other hand, is an actual projection of light. So our projectors that we used to use in face-to-face classes, those form real images because they use actual light projected onto a surface that then reflects that light. Another characteristic of mirrors is that they have what we call left to right reversal. So, if you take a selfie, your selfies will always be flipped from left to right. I'm raising my right hand now, but in the image on the camera, it's the left hand that looks like it's being raised. At least it's on your left side. So again, in mirror images, there's left and right reversal. Whenever the mirror is standing straight vertically, it's always flipped vertically. So it's flipped from left to right. But it doesn't flip up down on plane mirrors. So we say that the image is always upright. When you look at yourself in the mirror, you won't look like you're upside down. You're always standing upright. It's just the left and the right that are flipped from each other. So for plane mirrors, another aspect is that the image always has the same size and the same distance as the object. It doesn't look like it's farther away. It doesn't look like it's bigger or smaller than you. So plane mirrors always give a reflection that is more or less the same as you. All right. The only difference is the left and right reversal. So the distance and the size will always be the same as the object. Is there a way to predict image formation? Now, with geometry and math, mostly geometry, of course, there's a way to predict how images form. Especially with plane mirrors, it's very simple. So we use what is called ray tracing or ray diagrams in order to describe how light is reflected or refracted. For this session, we're going to focus on reflection of light. So how do we make a ray diagram for plane mirrors? First, we draw the object, arrow, mirror, and normal line. Then we trace rays from the tip of the arrow to the intersection of the normal and the mirror. Then we trace rays from the tip of the arrow to the mirror parallel to the normal line. Then we trace extended rays backwards from rays moving away from the mirror. Of course, that's complicated, so we're going to do this step by step with pictures. So first, we draw the object, the arrow, the mirror, and the normal line. So this is the object represented as an arrow. It's useful to draw objects as arrows so that we see where the base is. We see its orientation, whether it's upright or inverted. So the tip of the arrow is where we start with most of our light rays. The mirror will almost always be placed in the center, and the object is almost always placed on the left. The standard procedure is to place the object on the left. Now the normal line again is the line that's just perpendicular to the mirror, and we put the base of the object on the normal line. All right, so this is the basic no light rays yet ray diagram. Next step is to trace a ray from the tip of the arrow to the intersection of the normal line and the mirror. What that means is that we just go from the tip of the arrow to the point between the normal line and the mirror, basically the center of your entire ray diagram or the center of your mirror. And then we just bounce that off based on the law of reflection. We just have an equal angle there so that it just bounces off as a reflected ray. That's it. That's the second step. You just bounce it off the center of the mirror. Next, we have to trace a ray from the tip of the arrow and then make it parallel to the principal axis or the normal line. So we have to make it parallel to the normal line. So we just bounce a ray off the mirror. Of course, if it goes straight toward the mirror, it'll bounce straight off the mirror. We just make one single parallel line. So what happens there is that we have rays that are coming off of the mirror. So we have the reflected ray here and the reflected ray here. So if we trace backwards from the reflected rays, we have extended rays moving away from the mirror, forming the image on the other side. So again, since it's a virtual image, it seems to come off of the mirror so that it looks like the image is forming behind the mirror. And this is why that is the case, because we extend the reflected rays to behind the mirror. That's why it looks like there's an image forming behind the mirror. All right, so this is how you make a ray diagram for your plane mirrors. What if the mirror is not a flat plane though? If it's not flat, it's curved, it's a spherical mirror. So for curved or spherical mirrors, they tend to distort images. Sometimes that's useful. So this distortion of images is called aberration or spherical aberration, and sometimes that's useful because it allows us to see, for example, a wider image. If you've seen these kinds of mirrors that are they look like they're bulging out, usually in convenience stores, these allow a greater area to be seen through the mirror. So if you look at the mirror, you can see multiple aisles or multiple people, stuff like that. So there are uses for these things. So what are the types of curved mirrors and how do they affect how light is reflected? There are two main types of curved mirrors. First, there's the convex mirrors. They tend to bulge outward. So these are the mirrors you see in convenience stores and ATMs. So these are called diverging mirrors because they tend to make light spread off of their surface. Concave mirrors, on the other hand, are caving inward and tend to focus light. You see this on spoons and stuff like that. And they are called converging mirrors because they tend to focus light towards a certain point. So what are the parts of a curved or spherical mirror? How do we describe the parts of a curved mirror? So we have basically the P, C, and the F. So when we say the P, or the principal axis, it's just the line coming out of the center of the mirror. So the principal axis is very similar to the normal line. Let's just call it the normal horizontal line, the principal axis. Your C, the center of curvature, would be the center of the sphere. We extended the whole curved mirror. So if we made an entire sphere out of the curved mirror, the center of curvature is just the very center of that sphere. The focus, on the other hand, or F, is the point halfway between the mirror and the center of the curvature, or C. So F is just half of C. So if you look at the diagram here, it's literally just halfway between the mirror and the point C. And the focal length is just the distance between the mirror to the focus. All right, so that's the main parts, the P, C, and the F of your curved mirrors. So what happens to reflection? We know that there's what we call spherical aberration. So how do we actually show that that happens? How do curved mirrors change how reflection happens? See, there's two new rules. Let's start with concave mirrors, the spoon-like mirrors. So in concave mirrors, any incident ray traveling parallel to the principal axis will be reflected toward the focus. Any incident ray passing through the focus, on the other hand, will be reflected parallel to the principal axis. So what the heck does this mean? Let's go through this one by one again with pictures. So while we're talking about these pictures for the rules earlier, we're also going to study how to make a ray diagram for concave mirrors. So first we draw the object, arrow mirror, and principal axis. So this is actually the same steps as a plane mirror. There's just new steps based on the new rule. So in step number 2, you trace a ray from the tip of the arrow passing through the focus first. Step number 3, you trace a ray from the tip of the arrow parallel to the principal axis. And then step number 4 is basically just trying to draw an image arrow based on where the reflected rays intersect. Now we're gonna go through this one by one, as well as the rules earlier. So first step, also the first rule, we have your object arrow, we have your crappy drawn mirror here, and we have the center of curvature and the focus. So the first thing you have to do again is to create your incident rays. So we have two incident rays that follow the two new rules for concave mirrors. The first incident ray is the one that's going through the focus. So one ray passes through F and it hits the mirror on this side. So you just take a straight edge or a ruler or your line tool on your computer and you make it hit the mirror on the other side. The other ray will be parallel to the principal axis. It just means it's a straight horizontal line coming from the tip of the arrow towards the mirror. That's it. Next, once you trace the reflected rays, again, based on the two new rules of concave mirrors, if it starts out going through the focus, if your incident goes through the focus, then your reflected ray will become parallel. On the other hand, if your incident ray is parallel and it hits the mirror, then it will become reflected and go through the focus. Again, this is for concave mirrors, or mirrors that look like spoons. So it's just flipping. Parallel will go through the focus, and things that go through the focus will become parallel. And because of that, there's an intersection where the reflected rays go through. So that intersection will be the new tip of your final image. So that tip of your final image will be coming from, the base of your final image will be coming from the principal axis, and then it'll extend all the way to the intersection of your reflected rays. So here's the first case of your concave mirrors. In this case, the object is beyond your center of curvature. So if it's beyond C, we have an image that is real because the reflected rays actually reach it and make it. It's inverted because the arrow is pointing down, so it's flipped upside down. This is unlike plane mirrors, where plane mirrors, it's upright. In this case of concave mirrors, it's upside down, and it's smaller than the object. So it looks like it's smaller than the object. All right, so if you look at yourself through a spoon, in a certain way. It'll look like you have a smaller version of your face being reflected off of the spoon. So that this is the summary of 3 out of 5 cases for, sorry, concave mirrors, not convex, concave. So, again, object beyond C, the image is real, inverted, and small. If the object is directly at your center of curvature, it's real, inverted, and the exact same size based on our ray diagrams. And finally, if your object is between C and F, the image will become real, inverted, and actually magnified. It becomes bigger. So you can see here, if you make a parallel incident ray, it'll get reflected through the focus going there. An incident ray going through the focus, reflecting off of the mirror, will become parallel, making an image that is much bigger. Alright? So that's the 3 main cases for concave mirrors. What if the object is nearer than the focus or even at the point of focus? So these are the 2 extra cases for concave mirrors. So here's what happens when the object is closer than F. So if it's too close, your object, your image will become a virtual image. It will become an image that looks like it's behind the mirror. It'll look upright and it'll look magnified. So here's what happens to the rays. Your incident ray that's parallel to the principal axis will get reflected towards the focus. Now, again, in plane mirrors, we extend the ray behind the mirror so that we can get something that actually intersects. So we're going to extend it behind the mirror. On the other hand, your ray that's coming from the focus, going through the tip of the arrow, and then going to the mirror will be reflected so that it's parallel to the principal axis. Then we extend the ray behind it, forming your virtual image over here. All right? Next, if your object is directly at the point of focus, then there's no image formed at all. See, this is what happens to the rays. Your incident rays will hit the mirror, just like how we discussed based on the new rules, the 2 new rules. But when they're reflected, they become parallel to each other. So both of the reflected rays are parallel to each other, meaning they never intersect. If they never intersect, they will never form an image. The point of this is that for concave mirrors, there is a blind spot. There's always a blind spot where if you're just the right distance from a concave mirror, you won't be able to see yourself. What about for convex mirrors? How do they manipulate light? So for convex mirrors, these are the mirrors that bulge out, or the diverging mirrors. So the revised rules in this case, so the same rules for concave mirrors will be revised, just small tweaks for the convex mirrors. So number 1, any incident ray that's traveling parallel to the principal will reflect so that its extension will pass through the focus, while the incident ray that's passing through, that would have passed through the focus when reflected, will become parallel to the principal axis. So same concept, it's just that this time it's the extensions that we're focusing on. Because in convex mirrors, again, it's diverging. Alright, so we'll see that when we look at the pictures, when we study how to make a ray diagram for convex mirrors. So these are the same 4 steps in plane mirrors and in concave mirrors, but again, adjusted for the convex mirror. So again, we have tip of the arrow in the direction of the focus. We have another ray that we have to trace that's parallel to the principal axis, and then we have to look at the extended rays and where they intersect to see the actual image. Alright, so let's go through the step by step with pictures. So this is the first step with the incident rays traced. Okay, so the first step, you draw the object, you draw the mirror, you draw the principal axis. The second step, you draw the ray that's going to pass through the focus. So the focus of a convex mirror is on the other side of the object, or other side of the mirror based on the object. So you can see here that the focus is over here. If we continue the ray, it would go through the focus, but again, the mirror is in between. All right. On the other hand, the other ray that we have to trace would be from the tip of the arrow going to the mirror itself. So again, going from the tip of the arrow going to the mirror itself, parallel to the principal axis. So if we trace the reflected rays off of that, again, based on the 2 new rules that are revised for convex mirrors, your incident ray that goes towards the focus will be reflected parallel to the principal axis. Your incident ray that would be your incident ray that is parallel to the principal axis when reflected would be reflected in such a way that if you extend it, it would pass through the focus. Again, it bounces off, and if you extend it, it would go through the focus. Okay, so the extension will pass through the focus. Now, if you extend those rays so that you get the intersection behind the mirror, we get your final image. Now, your final image in this case, since it's behind the mirror, it's virtual. It's upright since your arrow will point upwards to go to the intersection, and it's smaller than the object. You can see here that it's literally a smaller arrow. So it's virtual, upright, and smaller. So do convex mirrors have different cases for images, just like with your 5 cases in concave mirrors? Are they that unpredictable? The answer is no. There's actually only one case for your convex mirror. Since the focus is on the other side, you can't have your object mirror or far, you can't have your object in different places or cases based on the focus. It's always away from the focus. So the only thing you have to remember for convex mirrors is that the closer the object is, the larger the image that forms. But the image will always be smaller than your object. So you can see here, your object placement number 1 will result in image number 1, the small arrow on the rightmost. While your object number 7, very close to the mirror, will have image number 7 here, still smaller, but significantly bigger than image number 1. So where's the math here? Sir, you said there's math in physics. How do we describe the lengths and the sizes of all of these things? What if my ruler sucks? Well, there's, of course, mathematical equations. There's 2 of them, actually. So we're going to get into the mathematical part of reflection. So first equation we have is the mirror equation. It relates the distances to the focal length. So this one, this equation just says 1 over f is equal to 1 over di plus 1 over do. Di is the object distance. Di is the image distance. Sorry, that's a typo there. It's the image distance. Do is the object distance, and f is the focal length. So once again, the tiny letter here is just the marker of its image or object. So if you know at least 2 of these, if you know the focal length or the image distance or the object distance, at least 2 of those, you can solve for the third thing. So in this diagram, we can see that the image distance is just the distance between the image and the mirror. The object distance is the distance between the object and the mirror. And the focal length is just the distance between the focal point and the mirror itself. So it's just the distances from the mirror. The second equation we need to know is the magnification equation. It relates the sizes to the distances. So the size of your object, how high your height of the object is compared to the height of your image. And again, it's just similar to the notation we had earlier. The subscript or the small letters are just reminders if it's referring to image or object. So h is the height or the size, so the height or size of the image or the object, again depending on the small letter. Whereas the d is the distance of the image or the object, once again. So take note that in the magnification equation, there's a negative sign for your di. All right, so because we have to take into account the fact that there's sign conventions in particular for your di. What does that mean? It means that for different placements of your object and your image, there are different signs that you have to use for the distance. So this is the sign convention we're talking about. Basically, if your mirror is in the center, to the left is negative, to the right is positive. Your arrow pointing up is positive, and your arrow pointing down is negative. It's very intuitive as long as you think of the mirror as the center. Sometimes your mirror will be placed to the extreme right of the ray diagram. Just think of the mirror as the new center. Again, left of the mirror is negative distance, right of the mirror is positive distance, up arrow is positive height, and down arrow is negative height. Again, this is if the object is written on the left. In all examples I will give, the object will always be written on the left, and when you draw your ray diagrams, always draw your object to the left of the mirror. So the math skills you need in order to be able to use these 2 formulas is basic algebra, integers, fractions, converting decimals into fractions just in case, and metric conversion just in case there are units that are given differently, like meters and centimeters. So in our exercises, I will allow you to use calculators, and you're allowed to use Google for your metric conversion. So your basic stuff that you need to get to have, your basic skills that you actually really need to have are your algebra, your integers, and your fractions. So how do we solve mirror problems? These are the steps. We draw the ray diagram, we take note of what's given, take note of what's being asked for, take note of the formula, and then solve them mathematically. So if you're familiar with the problem solving methods such as GAPSA or GRESA, which we might have taken up in previous years, then you're free to use that. In fact, I recommend that you use that for your partial points. So first, drawing the ray diagram. So let's take a sample problem. A Star Wars action figure 8 centimeters tall is placed 30 centimeters in front of a concave mirror with a focal length of 10 centimeters. Where's the image? How tall is it? And what are the characteristics of the image? So first, we'll draw the ray diagram. In order to get the ray diagram from a sample problem, we need to focus on making sure we get the right case. So again, when we talk about cases, we're talking about how far the object is from the mirror. So in the case of convex mirrors, there's only one case. You don't need to worry about it. You just have to make some willy-nilly diagram. On the other hand, for concave mirrors, that's the one with the multiple cases. So that's when you have to compare how far the object is compared to the focal length. In this case, the object is 30 centimeters from the mirror, and the focal length of the mirror is 10 centimeters. So we know that the object is farther than the focus. So when we make our ray diagram, we make the object far from the focus. All right. And if we have to see if it's on the center of curvature or not, we just multiply the focal length by 2. Once again, the focal length is just halfway between C. So if we take F, or 10 times 2, that's 20. 20 centimeters is the length to your center of curvature. So we know that your object is beyond the center of curvature because 30 is greater than 20. This gives us this ray diagram. All right, so it should look like this. So that's the ray diagram we're going to work with. Now, we're going to have to get the given from the sample problem. Basically, this means looking for the numbers and any hidden given that there may be. In this case, at least, all the numbers are given. There's no hidden given here, which is basically applying concepts to get numbers, more numbers. So in this case, we're given all the numbers. So we have the height of your object, 8 centimeters. So we say height of the object is 8 centimeters. We have the distance of your object from the mirror. So the distance of the object is equal to 30.0 centimeters. And your focal length is 10 centimeters. So it's all color-coded here. So the tip here is to understand what numbers are being described in the problem and what those numbers mean. Are they the focal length? Are they the height of the object or the height of the image? You need to be able to read and understand. Apply your English skills. Third step is, what is the question? What exactly is being asked for? So you have to look for the questions in your sample problem. In this case, there's actually 3 different questions. And when we say looking for the question or noting down what's being asked for, we're trying to find out what are the missing variables. So in this case, when it's asking where is the image, it's actually asking what is the image distance. So we're looking for DI. So that's the image distance. That's the first question. Next question is, how tall is the image? So that's the height of the image. So height of the image, that's the second thing we're looking for. And the third thing, what are the characteristics of the image? When we discussed image characteristics earlier, we were talking about whether they're real or virtual, whether they're upright or inverted, whether they're smaller or larger. So these are the questions that we need to ask. The smaller or larger will be answered by the ray diagram. All right. So fourth thing is we need to figure out what formulas to use to answer these questions. So the tip here is to use formulas that contain what is missing and what is given. So now that we have the given noted down in our array diagram and we know what's missing, let's list down the different formulas that we have. We have 2 formulas for mirrors. We have the mirror equation and the magnification equation. Now in this case, when we look for the missing variables, we have to see, I've color-coded it here. So what missing variables we have? We have DI, we have HI, and we also have to say if they're real, virtual, upright, or inverted. The 2 last questions will be solved by the ray diagram. DI and HI, on the other hand, you'll only find those. DI, it's easiest to solve using the mirror equation. If you try to solve for DI on the magnification equation, you'll have too many missing variables. So we'll start with the mirror equation. On the other hand, only the magnification equation has hi, or the height of the image. So we'll need both of these equations in order to answer all of our questions. And we start with the mirror equation because it has the missing variable and the given we need to solve for that missing variable. In this case, the magnification equation, we have the white color. The white color variables are things we have absolutely no idea about. So it's not a missing variable that's being asked for, and it's not in the given. So since we have two of those, we're not going to start with that. We're going to start with the mirror equation. So let's solve. So first things first, again, we started with the mirror equation. This is the mirror equation over here on the top left with the cursor. On the other hand, when we substitute our given, when we replace f with the value and the d0 with the value, we get this equation. Take note that before you substitute, you have to make sure that all of your units are the same. Again, we need to make sure all the units are the same. So checking, we have centimeters here, centimeters there, and centimeters down here. So all the units are the same. We just plug in all the numbers. So we have 1 over 10 is equal to 1 over di plus 1 over 30. So in the next step, we take this equation and then we transpose one of the terms. So we transpose 1 over 30 to the other side to isolate 1 over di. So again, we isolated di by moving 1 over 30 to the other side. We subtracted 1 over 30 from both sides of the equation. So we get this equation. Now we can't subtract these fractions because they're not similar fractions. So we need to make them similar fractions by getting the common denominator. We got that by multiplying 1 over 10 by 3 over 3. We get 3 over 30, which is an equivalent fraction to 1 over 10. So 3 over 30 minus 1 over 30, that we can actually subtract. So 3 minus 1 is 2. So we have 2 over 30 is equal to 1 over di. Now, if you have 1 over di and 2 over 30, we have to isolate di so that it's not 1 over di. Now, you can do this by cross-multiplying. You can do this by, basically cross-multiplying. So you multiply 2 by di and multiplying 1 by 30 and making those numerators. Or you can do the shortcut, which is just to flip both sides of the equation. So we flip this side. So 1 over di becomes di over 1. So we erase the 1 there because di over 1 is equal to di. So di divided by 1 is just di. And if we flip 2 over 30, we get 30 divided by 2. Now, if we do that, we get 15. So 15 centimeters is your image distance. So now we have our image distance. We've solved for di. Now, since we solved for di, we have it as a new given now, allowing us to solve for hi. So again, your answer for one question might be your given for the next one. So let's continue by using the magnification equation. So let's use the magnification equation. So here's the magnification equation, and we're going to plug in the values. In this case, m, or magnification, is not being asked for, and it's also not in the given. Right? So this is the given that we have here on the lower right. So since it's not part of the given and not part of the what's being asked for, we can just omit this part of the equation. So let's just erase m equals and just work with what we need. So hi over the height of the object, which is 8, is equal to negative 15, the image distance, over 30. So again, we have here di and we have here do. So we plug that in, we have hi over 8 is equal to negative 15 over 30. Now, in the next step, we took the simplest terms of negative 15 over 30. This is basically just negative 1/2. So since we have simplest terms there and we have hi over 8 here, we need to isolate hi. So to isolate hi as if it was x, we multiply both sides by 8 to cancel out the 8 here. So we have 8 divided by 8, that's just 1. And if we multiply 8 by negative 1/2, we get negative 4. Okay, so again, if we have 8 here, we just cancel that out, 1 and 4. 4 times negative 1 is negative 4. And that gives us our hi, our negative 4. So our hi, or our height of the image, is just 4 centimeters. And since it's negative, That negative means that it is inverted. Again, based on our sign conventions, a negative image means that it is inverted. So that gives us the answers to our questions. The image is 15 centimeters away from the mirror. It has a height of -4. It's real, inverted, and smaller than your object. So that is how you solve a problem regarding curved mirrors. So again, don't forget to try to use problem solving tips. Try to get all of the given from the problem and make sure to use the proper formulas in order to solve for your questions, the answers to your questions. So reflections, as you can see, especially with curved mirrors, they aren't always perfect. Sometimes the reflection is diffuse. Sometimes the image that is formed is virtual and not real. Case in point, who you are is within you. It's not some virtual image. So don't look in the mirror to see who you are. You have to look within yourself. So that's pretty much it for this topic. I'll see you guys next time.
That is over.